In the name of Allah, in this lecture, we will discuss the main components of the overhead electric power transmission system. Together, we will explore the different types of towers used in overhead electric power transmission lines, as well as the most important and well-known types of conductors used. We will also cover the key types of insulators utilized in the towers of overhead electric power transmission lines. Furthermore, we will learn the basis upon which a transmission line is determined, designed, or constructed. For example, a 66 kilovolts transmission line, a 220 kilovolts transmission line, or a 500 kilovolts transmission line. Accordingly, we will understand the criteria used to determine the required voltage level for the construction or design of an overhead electric power transmission line. At the beginning, we must understand that the primary objective of using and constructing overhead transmission lines is to transmit electric power or electrical energy from the power generation station and substations to the distribution networks or consumption areas in general. Of course, overhead transmission lines are typically used in main areas or desert regions, somewhat distant from crowded places, cities, or residential areas as much as possible. This is in contrast to power cables, which are naturally more suitable for densely populated areas or inside cities in general. It is very important to understand that each overhead transmission line has a specific voltage level on which the line is designed or constructed. We must know that the voltage of the transmission line or the rated voltage of the overhead transmission line is determined and selected based on two factors. The first factor is the length of the overhead transmission line in kilometers. The second factor is the amount of electric power that will be transmitted through the overhead transmission line, whether it is in megawatts or megavolt amperes. The second important point is that overhead transmission lines operating at voltage levels of 11 kilovolts, 22 kilovolts, and 33 kilovolts are classified as medium voltage lines. These lines are typically used in distribution networks or for transmitting electric power up to approximately 10 megawatts per circuit. However, overhead transmission lines operating at 66 kilovolts or 132 kilovolts are classified as high voltage lines. Meanwhile, transmission lines operating at 220 kilovolts, 400 kilovolts, and 500 kilovolts are classified as extra high voltage transmission lines. It is also important to note that there are transmission lines with voltages higher than the extra high voltage range. These lines operate at voltage levels such as 800 kilovolts and 1500 kilovolts and are referred to as ultra-high voltage transmission lines. These ultra-high voltage lines exist in certain countries such as Japan and Russia. Therefore, in conclusion, we must understand and emphasize the importance of knowing two key factors: the amount of electric power in megawatts that needs to be transmitted and the length of the transmission line in kilometers. Based on these two factors, we can determine the appropriate transmission voltage value in kilovolts for the overhead transmission line. Accordingly, we have understood that whenever the transmission voltage is high, this means that the transmission line is long, and the electric power to be transmitted will also be large. However, we now want to understand the main advantages or the benefits we gain from increasing the transmission line voltage to high values. So, why do we increase the transmission voltage to high levels? First, increasing the transmission voltage allows us to transfer more electric power between stations. Remember, electric power, represented by the letter S, is the result of multiplying voltage by current. Power equals voltage times current. That means if we raise the voltage, we automatically increase the power we can transfer. Second, by increasing the transmission voltage, we reduce the amount of current that flows through the transmission line. Again, since power is voltage times current, if the voltage goes up, the current goes down for the same power level. This also helps in reducing the voltage drop along the line, because voltage drop depends on current and resistance. So, less current means less voltage drop. Third, higher transmission voltage means lower power losses. Power losses in a line are calculated as 3 times the current squared times the resistance. So when the current is lower, the losses drop significantly. Fourth and finally, increasing the voltage can reduce the overall cost of the transmission line. That's because the size of the conductor or its cross-sectional area is directly related to the amount of current it carries. If we raise the voltage and lower the current, we can use smaller conductors, which means lower material costs and cheaper installation overall. It is also very important for us to quickly and briefly understand the main components of overhead transmission lines. To begin with, we must know that any overhead transmission line consists of three main elements, which are: first, the towers; second, the insulators; third, the conductors or different types of wires. We must also understand that the conductor or wire is the primary component of the overhead transmission line. The other components of the line are considered supporting elements, whose functions are to carry, tension, or mechanically support the conductor, and to insulate it from the ground. So now we know that the main components are the towers, conductors, and insulators. However, we should also know that there are some additional accessories or fittings used in overhead transmission lines, which include the following: earth wire or ground wire, also called shield wire; vibration dampers; spacers, used to maintain proper separation between conductors; guard rings, metallic rings used for corona control; and finally, marker balls, used as aerial warning devices for aircraft. These accessories play an important role in improving the mechanical stability, safety, and performance of the overhead transmission line. Before we explain in detail the components of the overhead transmission line and the function of each component or each part, we must first understand a very important point, which is the topic of the different clearances and distances in overhead transmission lines. This is because the design of the overhead line and even the design of the transmission tower itself is based on these various distances and clearances. The first point is the height of the tower, or the height of the conductors above the ground, which refers to the safe distances between the conductors and the ground, commonly known as ground clearance. To begin with, it is very important to understand that most transmission towers used in overhead transmission lines have heights ranging approximately from 15 to 50 meters, except in some special cases. For example, in some special cases of overhead transmission tower heights, we notice that the tallest two transmission towers in Egypt are approximately 221 meters high. These two towers are part of the 500 kilovolts overhead transmission line that crosses the Suez Canal. Naturally, this significant height is required to avoid interference with the large ships that pass through the Suez Canal. However, when we talk about the height of the tower of an overhead transmission line or the height of the conductors or wires above the ground under normal conditions, it is of course related to or based on the voltage level. And in order for the information to be accurate, we must understand that the height of the tower for an overhead transmission line with a voltage level of 66 kilovolts located in desert areas or open spaces will definitely be different from the height of a 66 kilovolts tower located near highways, where there is continuous traffic and movement of vehicles, transport trucks, and heavy equipment. However, in general, we find that international standard specifications have defined the minimum clearance height of conductors above the ground according to the voltage level, and of course, after taking into consideration the study of conductor sag. For example, in the case of an overhead line with a voltage level of 66 kilovolts, the height of the nearest point of the closest conductor from the ground must not be less than 6 meters. In the case of an overhead line with a voltage level of 132 kilovolts, the height of the nearest point of the closest conductor from the ground must not be less than 6.5 meters. In the case of a voltage level of 220 kilovolts, the height of the nearest point of the closest conductor from the ground must not be less than 7 meters. Finally, in the case of a voltage level of 500 kilovolts, the height of the nearest point of the closest conductor from the ground must not be less than 9 meters. The second point is the vertical distance between the conductors themselves, or the minimum vertical clearance between the conductors or between the phases. Accordingly, we find that in the case of an overhead line with a voltage level of 66 kilovolts, the minimum vertical distance or vertical clearance between the conductors or between the wires must not be less than 2.2 meters. In the case of an overhead line with a voltage level of 132 kilovolts, the vertical clearance between the conductors must not be less than 2.8 meters. In the case of an overhead line with a voltage level of 220 kilovolts, the vertical clearance between the phases must not be less than 3.3 meters. Finally, in the case of an overhead line with a voltage level of 500 kilovolts, the vertical clearance between the phases must not be less than 5.5 meters. The third point is the horizontal distance between the conductors or between the phases or between the wires of overhead transmission lines. In the case of an overhead line with a voltage level of 66 kilovolts, the minimum horizontal distance or minimum horizontal clearance between the conductors or between the phases must not be less than 5 meters. In the case of an overhead line with a voltage level of 132 kilovolts, the horizontal distance between the phases must not be less than 6 meters. In the case of an overhead line with a voltage level of 220 kilovolts, the horizontal distance or minimum horizontal clearance between the conductors or between the phases must not be less than 9.8 meters. In the case of an overhead line with a voltage level of 500 kilovolts, the minimum horizontal distance or minimum horizontal clearance between the conductors or between the phases must not be less than 15.5 meters. The fourth point is the distance between the towers of overhead transmission lines along the length of the transmission line or the distance between one tower and the next. This is what we refer to as the span. For example, in the case of an overhead line with a voltage level of 66 kilovolts, the distance between one tower and the next is approximately 250 meters. In the case of an overhead line with a voltage level of 220 kilovolts, the distance between one tower and the next is approximately 330 meters. In the case of an overhead line with a voltage level of 500 kilovolts, the distance between one tower and the next is approximately 400 meters. The fifth point, or the final point, is the right-of-way width of overhead transmission lines. Of course, there must be sufficient safety clearances on both sides of the overhead line, and these distances can be measured either from the center line of the overhead line to each side or as the full total width as shown in the image in front of us. For example, the right-of-way width for an overhead line with a voltage level of 66 kilovolts must not be less than 26 meters, or in other words, not less than 13 meters from the center line of the overhead line to each side. Also, the right-of-way width for an overhead line with a voltage level of 132 kilovolts or 220 kilovolts must not be less than 50 meters or not less than 25 meters from the center line to each side. In the case of an overhead line with a voltage level of 500 kilovolts, the right-of-way width must not be less than 70 meters or 35 meters from the center line to each side. Let us begin together and briefly with an explanation of the main components of the overhead transmission line system. The first component is the towers. The primary purpose of overhead transmission line towers is to carry and tension the conductors, wires, or phases in general. These towers must ensure that the conductors are maintained at a suitable and safe height above the ground. In addition, the towers must also ensure adequate safety clearances between the phases themselves. In other words, we must understand that the design of towers for overhead transmission lines is based on several different factors, which are: first, the rated voltage level. Of course, the design of a tower for an overhead transmission line with a voltage level of 66 kilovolts will definitely differ from the design of a tower for a line with a voltage level of 220 kilovolts or 500 kilovolts. Second, the number of circuits that the overhead transmission line tower carries. Third, the distance between the towers. Fourth, the climatic factors that the transmission line is exposed to, such as wind, floods, snow, and so on. Fifth, the diameter of the conductors and the spacing between them. Finally, the geographical factors, such as the nature of the terrain. But what are the types of towers used in overhead transmission lines? Suspension towers, tension towers, transposition towers, terminal towers, used at the beginning and end of the line. Angle towers, used for direction change or route adjustment. crossing towers, used for special crossings. And in order to understand the types of towers used in overhead transmission lines, we must know that the type of tower is determined based on the method of insulator installation and the function of the tower. In other words, if the insulator mounted on the transmission line tower is a suspension insulator, this means that the tower will be a suspension tower. If the insulator mounted on the tower is a tension insulator, this indicates that the tower will be a tension tower, and so on. The first type of tower used in overhead transmission lines is the suspension tower. It is important to understand that suspension towers used in overhead transmission lines constitute approximately 75% to 80% of the total number of towers along the transmission line. The function of suspension towers is to carry the conductors or phases only, meaning that these towers are not subjected to any horizontal tensile forces at all. Therefore, we must understand that in the event of any emergency, if any conductor falls from one side, we will observe that all the conductors on all the adjacent suspension towers will be affected by the fall of that conductor. To avoid this from happening and to prevent the conductors from collapsing across all the suspension towers, a tension tower is used after approximately every 10 suspension towers. The second type of tower used in overhead transmission lines is the tension tower. The primary function of tension towers is to withstand mechanical tensile forces. From the diagram in front of us, we can identify the tension tower. In other words, we notice that a tension tower is characterized by having two strings of insulators at each attachment point on the tower. This means that the first string of insulators is used to connect the conductor to the tower and the previous tower, while the second string is used to connect the conductor to the tower and the following tower. If we observe closely, we find that the phase or conductor is interrupted by the tension insulators, which is why we notice the presence of a conductor connecting the ends of the tension insulators. This is known as a bridle. And as I mentioned earlier, approximately after every 10 suspension towers, a tension tower is installed. This is done to prevent the conductor, wire, or phases from collapsing from all the towers in case of any emergency situation, such as a breakage in one of the conductors, especially since the majority of towers along the transmission line are suspension towers. Next are the transposition towers. At the beginning, it is very important to understand that the primary function of transposition towers is to interchange the three phases R, S, and T at equal distances along the length of the overhead transmission line. But why are these conductors or phases R, S, and T interchanged? Of course, we all know that each conductor carries an electric current, and due to the flow of electric current within the conductor, along with the presence of frequency, this results in the presence of inductance, and this is the first point. The second point is that we must understand that there is a voltage difference between each pair of conductors or between each pair of phases. Due to the existence of this voltage difference, along with the frequency, this results in the presence of capacitance. This means that there is capacitance between each pair of phases and also capacitance between each phase and the ground. Naturally, since the phases are vertically arranged above one another, the capacitance between the first phase R and the ground differs from the capacitance between the second phase S and the ground, and also differs from the capacitance between the third phase T and the ground. Therefore, we must understand that the values of both capacitance and inductance depend on the tower dimensions and the height of the conductors or phases above the ground. Hence, the function of transposition towers is to interchange the phases along the transmission line in order to equalize the inductance and capacitance of the three phases R, S, and T throughout the length of the transmission line. That is why, when we use transposition towers, there must be either three such towers along the transmission line or multiples of three, such as 6 towers or 9 towers, and so on. But why is that necessary? Of course, it is to maintain the correct phase sequence with the first phase R followed by the second phase S, then the third phase T, at both the beginning and the end of the overhead transmission line. This means that, for example, the phase R at the beginning of the transmission line is the topmost phase in the overhead transmission line. Then, by using the first transposition tower, we notice that phase R has shifted to the middle position. That is, it has become the second phase. By using the second transposition tower, we observe that phase R has moved to the bottom position among the phases. Then, by using the third transposition tower, we notice that phase R has returned once again to the top position among the phases in the overhead transmission line. It is important to emphasize that the transposition towers must be installed at equal distances along the overhead transmission line. For example, if the overhead transmission line is 150 kilometers long and we are going to use 3 transposition towers, then a transposition tower should be installed every 50 kilometers. And of course, we must emphasize and understand that the transposition tower is, in essence, a tension tower. Now let's talk about angle towers. Definition: angle towers are special types of transmission line towers that are used when the transmission line needs to change direction. This could be a horizontal turn, like turning left or right, or a vertical change, such as going up or down over hills or uneven terrain. Purpose: first, route adjustment. Angle towers help the transmission line navigate around obstacles or follow the natural contours of the land. Second, mechanical stability. Because the line changes direction at these points, angle towers are built to withstand the unbalanced forces created by the pull of the conductors in different directions. Key features: they are generally heavier and stronger than regular straight towers. Instead of suspension insulators, angle towers use strain insulators, which are better suited for handling directional tension. They are also designed to handle greater side loads caused by the angular deviation of the conductors. Typical uses: you'll find angle towers at points where the line turns, say at angles of 30, 60, or even 90 degrees. They're also common in rugged or hilly areas where the alignment of the transmission line needs to shift frequently. And finally, in urban or crowded environments, angle towers help guide the line safely around buildings and other obstacles. Next, let's talk about terminal towers. Definition: terminal towers, also known as dead-end towers, are used at the beginning and end of a transmission line. They serve as the anchoring points where the line either starts from a substation or ends at another terminal, like a substation or distribution point. Purpose: their main job is to terminate the transmission line. They provide strong mechanical support to handle the full tension of the conductors, since there is no continuation of the line in one direction. They also allow for easy connection to substations or switching stations. Key features: terminal towers are built to be extra strong because they bear the entire pulling force of the conductors from one side. They are equipped with strain insulators to safely manage this tension. Additionally, they often have attachments or fittings for connecting to equipment inside substations. Typical uses: you'll find terminal towers at the start and end points of a transmission route. They're also used at intermediate switching stations, or where the line ends at a load center or a transformer substation. Now let's look at crossing towers. Definition: crossing towers are a special type of transmission tower used when the line needs to pass over obstacles such as rivers, highways, railways, or valleys. These towers are designed to provide extra clearance and safety in such situations. Purpose: their main role is to ensure the transmission line can safely cross over areas where ground clearance is critical. They also help maintain proper mechanical tension across long spans, which are common in crossing situations. Key features: crossing towers are typically taller than standard towers to provide the required clearance. They are often built in pairs, one on each side of the crossing. Due to the longer spans involved, they are designed to handle greater conductor tension and wind loading. Typical uses: you'll see crossing towers at locations such as river crossings, where the line must span wide water bodies, highway or railway crossings, where clearance regulations must be strictly followed, deep valleys or gorges, where extra height and strength are needed to bridge the gap. The second component or part of the overhead transmission line is the insulators. At the beginning, it is very important to understand that the primary function of the overhead line insulators is, first, an electrical function, which is to provide electrical insulation between the conductors or phases from each other and between the phases and the body of the tower. Second, a mechanical function, which is to support and hold the conductors or the wires or the phases in general along the length of the transmission line. The second important point we need to understand is that the insulators used in overhead transmission lines consist of a set of discs, and of course, these discs are assembled and arranged together to form what is known as the insulator string, as clearly shown in the image. But the important question is, approximately how many discs does an insulator string consist of? It is important to understand that the number of discs in an insulator string or the number of insulator units depends on the transmission line voltage. In other words, as the voltage increases, we will certainly observe an increase in the number of discs in the insulator string. For example, in the case of 66 kilovolts, the insulator string consists of approximately 6 discs. In the case of 132 kilovolts, the insulator string contains approximately 10 discs. For 220 kilovolts, the insulator string typically includes around 12 discs. And finally, in the case of 500 kilovolts, the insulator string may contain approximately 24 discs. However, as we can see, in some situations, 2 insulator strings are used in parallel to support the conductor. This occurs when the mechanical load on a single insulator string is too high. Therefore, it becomes necessary to use 2 parallel insulator strings to share the mechanical load. Therefore, we need to understand together what are the types or the most important types of insulators used in overhead transmission lines. The first type is the porcelain insulators. The second type is the glass insulators. The third type is the silicone rubber insulators. In the image in front of us, we see the shape of a porcelain insulator, and of course, a group of the discs shown here are assembled to form an insulator string as shown in the image. The second type of insulators is the glass insulators. It is very important to understand that the main disadvantage of glass insulators is the ease of moisture condensation on the surface of the glass insulator. This means that a flashover can easily occur when there is dust present on the insulator's surface. For this reason, as much as possible, the installation of glass insulators should be avoided in humid locations. The third type of insulators is the silicone rubber insulators. Of course, the most important advantage of these rubber insulators is that they are lightweight. Another key advantage is their hydrophobic property, meaning that it is difficult for water or moisture to accumulate on the surface of this rubber insulator. As a result, the occurrence of flashover or any electrical sparking is greatly reduced. God willing, in a future lecture, we will discuss and explain in more detail these insulators, their characteristics, and the advantages and disadvantages of each type of insulator. Next, we come to the third component of the overhead transmission line, which is the conductor. It is very important to understand that the conductor or the wire is the main component in the overhead transmission line. In other words, it is the primary part responsible for transmitting electrical power or electrical energy from one location to another. Of course, the conductors or wires used in overhead transmission lines are bare conductors, meaning they are not covered with any insulating material. In an upcoming lecture, we will discuss in more detail the types or the most common types of overhead transmission line conductors, their characteristics, as well as the advantages and disadvantages of each type. However, for now, we will briefly explain the most important or most well-known types of conductors used in overhead transmission lines. The first and most well-known type of conductor used in overhead transmission lines is the aluminum conductor steel reinforced, ACSR. The aluminum conductor steel reinforced, ACSR, consists of a core made up of one or more layers of galvanized steel wires, with one or more layers of aluminum wires wound over it. That is why we often find the cross-sectional area of this type of conductor expressed as 2 numbers. For example, 350 square millimeters, which means that the cross-sectional area of the galvanized steel wires is 50 square millimeters, and the cross-sectional area of the aluminum wires is 380 square millimeters, and so on. Another important point is that aluminum conductor steel reinforced, ACSR, conductors can withstand temperatures up to 80 degrees Celsius only. The second type of conductor used in overhead transmission lines is the all-aluminum alloy conductor, AAAC. This type consists of an alloy made from aluminum, magnesium, and silicon. One of the main advantages of all aluminum alloy conductor, AAAC, is that it has a lower electrical resistance compared to aluminum conductor steel reinforced, ACSR. Of course, this means lower electrical losses. Another very important point to note is that all aluminum alloy conductor, AAAC, can withstand temperatures up to 90 degrees Celsius. The third type of conductor used in overhead transmission lines is the heat-resistant conductors. The most important advantage of these conductors is that they can withstand temperatures up to 210 degrees Celsius without losing their properties. The most well-known type of this category is the super thermal resistant aluminum alloy conductor INVAR reinforced, STACIR. The core of this conductor is made of INVAR, and it is important to understand that INVAR is an abbreviation for invariable to change of temperature, meaning that the core of this conductor, which is INVAR, does not change its properties with the rise in temperature. Another important point is that the core of the conductor, which is INVAR, is an alloy composed of iron and nickel, and it does not expand with heat or get affected by temperature. We will now talk about the most important accessories or fittings used in overhead transmission lines, in addition to conductors and insulators. The first type of accessory or fitting used in overhead transmission lines is the ground wire or earth conductor. The ground wire or earth conductor is installed at the highest point of the overhead transmission tower, running along the entire path of the overhead line. This ground wire is usually made of galvanized steel, and of course, we all know that all these towers are earthed. This means that the ground wire is connected to the earth through the structure of the tower itself. The ground wire is used to protect the towers, conductors, and insulators from lightning strikes by discharging the lightning current to the ground through the tower structure. However, it is important to note that the ground wire used nowadays is often of the optical ground wire, OPGW type, which serves two functions. The first function is protection against lightning strikes. The second function is to transmit data, signals, or communication between different substations or between the substations and the control center. As we can see, some towers or some overhead transmission lines have only one ground wire installed, while other lines or towers have two ground wires. This is done to provide complete protection for the insulators in the overhead transmission line. We will discuss this specific point in more detail in an upcoming lecture. We now move on to another important component of the accessories or fittings used in overhead transmission lines, which is the spacers. When we mention spacers for conductors, this indicates that a single phase consists of more than one conductor. This is what we refer to as the bundled conductor system, where a single phase may consist of one conductor, two conductors, three conductors, or even more. This applies to each phase. Therefore, we must use these spacers between the conductors of a single phase to ensure a fixed and uniform distance is maintained between these conductors along the length of the transmission line. The second important point to note is that we also use these spacers in the bundled conductor system to help reduce the effects of the corona phenomenon as well as the skin effect present in overhead transmission lines. This is achieved by increasing the effective cross-sectional area of a single phase through the use of multiple conductors, that is, bundled conductors. We now move on to the third component of the accessories used in overhead transmission lines, which is the damper. Overhead transmission lines are constantly exposed to strong winds, and these strong winds can cause the conductor and insulators to vibrate. Such intense vibrations can potentially lead to conductor breakage at the point where the conductor is suspended from the insulator. For this reason, dampers are used to reduce the mechanical stress on the conductor and to prevent vibrations that may lead to the collapse of the transmission tower. It is very important to know that there are two main types of dampers. One, Stockbridge dampers, which consist of a short cable with weights, either concrete or metallic masses, attached at both ends. These dampers are typically installed at the beginning and end of each conductor span between two towers. 2. Spiral vibration dampers, which consist of a heavy wire that is coiled around the conductor in a spiral shape similar to a spring. These types of dampers are essential for ensuring the stability and longevity of overhead transmission lines under windy conditions. We now move on to the fourth component of the accessories or fittings found in overhead transmission lines, which is the guard ring or metallic ring. The insulator string consists of a number of discs, and each disc is made up of an insulating part and a metal pin. This means that the entire insulator string is composed of insulating materials and conductive parts, which in turn means that the insulator string behaves like a series of capacitors. A noticeable issue arises from this structure, which is the unequal capacitance or unequal voltage distribution across the discs of the insulator string. Specifically, the disc closest to the conductor is subjected to the highest voltage or electrical stress, while the discs farther from the conductor are subjected to lower voltages. This leads to a non-uniform voltage distribution along the insulator string. To solve this problem, guard rings or metallic rings are used to redistribute the electrical voltage equally across all the discs in the insulator string of the overhead transmission line. By doing this, the problem of unequal capacitive effects along the insulator string, which causes non-uniform voltage distribution, is resolved. The fifth component of the accessories used in overhead transmission lines is the warning spheres for aircraft, also known as warning balls or warning lights. These warning spheres are typically installed in areas where aircraft frequently pass or in locations near airports. Their main purpose is to make the overhead transmission lines more visible to pilots, especially in low visibility conditions, in order to prevent any potential collisions between aircraft and the transmission lines. Thank you for your attention. See you in the next lecture.